Welcome, my dear students, to our physics lesson. It's me, Mr. Samuel John, your physics teacher. Our today's discussion will be talking on the topic known as vibrations and waves, but subtopic known as interference. So our discussion here, we have the topic vibrations and wave. Our subtopic, it's interference. Interference of the waves. So, this is the topic that is very interesting to our lives. And most of the students, you know, there are different ways of producing interference. But before we discuss this kind of interference, which is now as a part of the physical properties of the wave, let's see now what are the applications of the waves in our lives. Interference, particularly even general waves itself, it can be applied in different fields of our life. For example, in medicine, waves is applied in ultrasound. When these waves are sent to the womb, they can be able to detect the development of the fetus. So from there, the doctors, they may know the progress of the fetus while in the womb. That's the first area where these waves can be applied. But the second area where we can apply this kind of interference, or the wave itself, generally can be applied in the speed trap. If you see most of the traffics on the road, they have the device that is normally used to detect the speed of the incoming cars. That is the application of the waves. The waves are sent from that devices to the incoming cars, and then those reflected waves will be able now to use it to determine the speed at which the car is moving. That's one area where waves can be applied. Third, waves is applied in the engineering. When the people are designing the board of the airplanes, most of the airplanes you see around the world, they are making use of the concept of waves. They means finding a way of reducing the intensity of light inside the plane. So that's how waves can be applied in our lives. So those are a few areas where waves can be applied. So you can see now the importance of these waves, and for today's discussion, it will be very interesting. So to discuss about the waves, let's start finding the method of producing interference. Before we proceed, you remember we did these parts in your classes. We found that there are different ways of producing interference. One of these methods is by using Young's double-slit experiment. Then, air wedge experiment. Third, we have Newton ring experiment. Then you can have interference from the thin films. So those are methods where you can use to produce interference. But our today's discussion will be based on the double-slit experiments, and from there we're going to see the formulas that are normally used in determining some of the parameters we use in waves. So to start with, number one, for these subtopics, we have said we have method number one, which is Young double-slit experiment. What is the Young's double-slit experiment? This is an experiment that was conducted by Young, and he used it double slits. The arrangement was, if you remember, we had a source here of light, the light source. It was given the name the slit source, and that's where the waves are coming from, that source. And then we have another arrangement, we have now the double slits arranged here, S1, S2. That's where the screen is. So the waves originating from here, we go to this to be passing through the different sources S1 and 2. So these are two sources we call coherent source. After passing here, they will form a pattern like that. This one. These kind of interfere. They interfere. When they interfere, that's where the screen, the image of the interference of the image will be formed on the screen. So the image, the way it was observed by Young, he saw a series of bright and dark fringes. That's why, very interesting. Now, from this arrangement, you see that one of the conditions to produce interference, you must have the two coherent source. This how can you produce the coherent source? It is produced from the source, which is given the name, is a monochromatic light. The light which has one wavelength. Now, from this experiment, you can see the patterns produced there. But let's see now, draw the diagram for this. We have, that is S1, this is S2, this is our screen, that is the center of the screen. One wave is coming here, another wave is coming here, so they meet somewhere here. Another wave is coming here, they normally meet. Another wave is coming from two sources, they meet somewhere. And then so the observation is the two sources, which are given the name of the coherent sources, produce light which they normally produce the patterns on the screen. And it has been observed that the central part of the screen is bright. So the images or the fringes are formed on either side of the center. And then from here we have the dark, and then you have bright, and then you have dark, and then you have bright. So there is a series of dark and bright fringes on the screen, according to Young's experiment. And those fringes are equal space. It means the distance from one fringe is the same. The width, the fringe width. Sometimes you use Y. The distance here is the same. The separation is because that's the separation, this fringe separation, or fringe width. So according to what we did about the Young's experiment is that he observed a series of bright and dark fringes in the screen, and these fringes were equal spaced. Very interesting. He was interested now. Want to see how do you find the formula which connects the distance from the center of interference to the first dark or the second dark. And then from there you can see how do you find the fringe separation. And to remind you what we did, you discussed that the distance here we call as y, n. The distance, for example here, the distance from the center, from here, that's our bright, center of interference to the second bright or nth bright. So we can use that as n. N stands for the order of the fringes, either dark or bright. So that is the letter used for fringe position, or use xn, the position of the fringes from the center. Now, because if you remember, we have two types of the interference which can be produced here, which we talk of dark or bright. We use other names, constructive and destructive. Constructive means bright fringes, and destructive means dark fringes. So let's find now the condition, the formula for finding bright fringes. The formula says it is n lambda d over small d. This is the position, the distance of the n bright fringes from the center. And we, as we have, and then we have for dark fringes, that's n, that's y equals to n plus a half lambda d over d. So now the two formulas are used to determine the position of the fringes from the center. But you should know the central part of the screen, that's where the bright fringe is formed. So when you're talking about the position of the bright fringes, the first order, that means when n equals to 0, we have the first bright image, which is now given the name the central bright, and then followed by 1, 2, and so on. And here the order is n equals to 0, 1, 2, and so on. Now the problem here, most of the students fail to distinguish how to use these orders. For example, when the question is talking about find the position of the first bright from the center, so this from the central bright, so this is not counted. We count this as our reference. So the first bright will be here. So our n equals to 1. When n equals to 2, we get the position of the second. When n equals to 3, we get the third bright fringes from the central fringe. But for dark fringe, because you know the problem here is at the center where the bright is. When you're finding the position of the dark fringes from the center, we know that the first bright, so the first dark, is formed when n equals to 0. And the second is n equals to 1. So you can see that the difference here, the first bright from the central fringe is formed when n equals to 1. Because when n equals to 0, we get this is the central fringe. So we don't count that. So those are the formulas that we did. At least you should know and you should be comfortable when you are using those two formulas for position of the bright fringe or dark fringe. That's how you can find the position. But also, we're going to see how do you find the distance between two successive bright or two successive dark. And you have seen from the experiment, according to Young's experiment, these fringes were equal spaced. It means the distance from the first dark, the second, are the same as the distance from the first to the second bright. Here, the same as y here. Now, what will be the formula for finding the fringe separation? The formula is simple. You can use any formula method. You can use either for bright or dark to derive the formula for fringe separation. Let's base on the bright to find the fringe separation. Sometimes given the name the fringe width. The width of the fringes. So for brights, let's find this is the position of nth bright, which is given by n lambda d over d. That's equation number 1. For example, this n can be 10, the position of the order of 10. Then next, after this, we'll be having n plus 1. Maybe if this is the second, so the third. The next will be n plus 1, lambda over d. And then there's the question number 2. We want to find the formula for the fringe separation. So the distance between two fringes here. The center is here. This distance here, maybe this is y1, y2 maybe. And this is now the distance from here is y3. So we want to find the distance between these two fringes, either dark or bright. So you find the difference here, yn minus yn plus 1 minus yn equals, this will be n plus d over 2, d, small d of this n plus 1 lambda d over small d minus lambda d over small d. So if you open the brackets, this will be n lambda d plus lambda d over everything will be under the same denominator minus n lambda d. This we cancel out, so remain with the lambda d over small d. So that is the formula for the fringe separation. That's more we use for y. This is yn plus this yn, y sub n. This denotes the position of the fringes. I've used the formula for bright. If you apply the formula for the dark, the formula for the fringe separation will be the same. So from here, we have y as n as lambda d over small d. And we know yn equals to n lambda d, yn equals to lambda plus a half d. This is for bright, this is for dark. So you should know, when you're looking for the position of the bright and dark, these are the two formulas to use. When you're looking for the fringe separation, this is the formula. Separation of the fringes. The formulas must be known and how to use them. So today's discussion, after observing the pattern which are formed by Young's double experiment, and you have seen the formulas which is normally used to find the fringe separation and the position of the bright and dark fringes from the central fringe. Sometimes that central fringe is given the name the center of interference. Let's turn our attention now to example number 1. The question is, in Young's double experiment, the slit separation is 0.2 millimeter. That means the distance between the slits. And the light of wavelength 6 times -7 is used, such that the fringes are formed on the screen, which is at 0.8 meters from the double slit. We are looking for the distance of the second dark fringe from the central. Now, we have seen the formula. So for dark fringe, the dark fringes, the formula says that yn equals to n plus a half lambda capital D over small d. And where n starts from 0, 1, 2, and so on. So the first image is found when n equals to 0, because the center, that's where you have the bright fringe. So this is where you have the first image, this is where you have the second image, and so on. So the formula is correct, but you may be having the correct formula, but fail to get the correct answer because you don't know how to use the orders. So here our n equals to 1. So y1 equals to 1 plus a half lambda d over small d. We are given that the wavelength is 6 times 10 -7 meter. The distance between the double slits to the screen is 0.8 meters, and the separation of the slits is at 0.2 millimeter, which is times 10 -3 meters. So this is now giving us 1 equals to 1 plus a half is 3 over 2 lambda d over that. So if you plug the values, this is 6 times 10 -7 times 0.8. So from here we can have y1 equals to 1 plus a half is 3 over 2 lambda d over small d. So you plug the values, this will be 3 times lambda, 6 times 10 -7. Our d, capital D, is 0.8 over 2 times 0.2 times 10 -3. So you can find the value of y1. That's y1 here equals to 3 times 10 power 3 times 6 10 -7. This is 0. It's 8 now. 8 times 10 -1. So if you use a calculator, and this will be 2 times 10 -1, and this will be -4, power -4. This 2 and 2 will be 4. 8 divided by 4 get 2. So this will be 3 times 6, 18, times 2, 36, times 10 -8 over 10 -4. This is 36 times 10 -4. If you combine there, so y1 equals to 3.6 times 10 -3 meters, or because that is a very small distance, that is given as 3.6 millimeter. So that's how you can find the fringe separation. So you can find the distance of the dark fringe depending the order. So this is the second dark fringe from the central fringe, and you have seen that the formula is known, but you should know how to choose the order. So choose the order from n equal to 0, that's the first order, and so on. That was the first part of that question. Find the distance of the second dark fringe. Choose the formula, apply the correct order, and then you come up with the correct answer. Part B, determine the distance of the second bright. Now for bright, if you remember, that's where you have to check closely. We know that the formula for bright fringes, fringes, distance yn is the same as n lambda d over small d. The n starts from 0, 1, so on. Now we know this is the central fringe, that's where we start counting from, the central fringe. So the first image is found when n equals to 1, the second when n equals to 2. First, second. For this case now, since we're looking for the distance of the second bright from the central fringe, our n should be equal to 2. N equals to 2, and this will be y2 equals to 2 lambda capital D over small d. We have 2, our lambda is the same as 6 times 10 negative 7. The distance between the screen and the double slit is given as 0.8. The slit separation was given as 0.2 times 10 negative 3. You convert into meter. So from there you use your calculator, or you take it normal arithmetic. This is times 10 negative 7. This is times 8 times 10 negative 1. This is 2 times 10 negative 4. Convert this one. So this will be, this 2 and 2 cancel out. So you have, this will be 6 times 8, 48. 8 times 10 negative 8 divided by 10 negative 4. This is 48 times 10 negative 4, which is the same as 4.8 millimeter. It's 4.8 times 10 negative 3 meter. So you know this is equals to millimeter. So we can see now the formula are well known, but the problem is how to choose the order. That's the end of the example 1. Question number 2. In question number 2, one of the use of Young double experiment is to determine the fringe width. Of course, you have seen that if you use this experiment and you have the traveling microscope, you can be able to see the position of the fringes, the position of the fringes from the center, and even you can be able to see the distance between two successive fringes. So you should know, you should have the monochromatic light of a known wavelength. The question now, the question says, suggest. That's one of the experiments we have seen here. This is one of the experiments we normally use to find the width. You talk about the fringe separation of the fringes, or sometimes these are given the image. Now, part A suggests how the fringe width of the images produced can be increased. Suggests how the fringe width of images produced can be increased. That's a very interesting question. How do you increase the fringe, the distance from the two successive fringes? That's the question is talking about. Method, ways of increasing that distance. So remember, from this formula of the fringe width is given by lambda d over that. That's where you should focus on. The focus should be done here when you are talking about the fringe width. So the parameters that will be modified to increase that y is lambda. One way of increasing the fringe width is to use the wavelength, the light of a longer wavelength. Why do we use long wavelength, not shorter? Because you know mathematically this y is proportional to the wavelength. If you use the short wavelength, you're reducing the fringe separation. So one way of increasing the fringe separation is to find or to apply in the experiment the source of light which has the longer wavelength. The second point is that you can see the distance from the slit to the screen must be changed. How? You increase the distance from the slits to the screen. You have to find a way of increasing, not the order of increasing, but when you reduce the distance, that y also decreases. So the second factor is to increase the distance from the slit to the screen, a considerable distance. Point number 3 is the slit separation. So that value should be reduced. You reduce the slit separation. So mathematically, we know that y is inversely proportional to that d. Inversely proportional means when you have a small distance, the fringe separation will be increasing. Fringe separation is direct proportional here. Y is proportional to the wavelength, but here, y is proportional to d. So the factors, they are depending how the fringe separation relates to d, lambda, and small d. That's our first part. The second part is, if the monochromatic light use it, yes, we had a monochromatic light whose wavelength is given. Now suppose this wavelength is replaced by another source, white light. And we said the monochromatic light is the light which consists of a single color. But when we talk of white light, it consists of 7 colors. What will be the appearance of the fringes when observed in this experiment? So we know that from the light, we talk of white light, visible light. We have these colors. We have red. These are the 7 colors that you have. So when we talk of, this is what you call white. But our eyes are not sensitive to all of these colors. Our eyes are only sensitive to the basic colors that we have: red, blue, and green. These are the basic colors of light. So we'll be able to see blue, green, and red. Now, what will be the appearance of the fringes? And if you remember in the experiment, we say when you use the monochromatic light, we're supposed to see the patterns of bright and dark fringes. The bright, not necessarily to be white, the brightness can be either bright of different colors. If you use monochromatic light, which is red or which is blue, so it means the intensity of that bright will be observed. And sometimes we don't have intensity, we reduce it to 0. We talk of now dark. Now, the question is now, how can you explain about these effects when we don't have monochromatic light, but we have white light? So from the concept that we know here, if you remember, when you move around that visible light, this side, so the wavelength increases when you go this way. In other words, frequency decreases. So red has the longer wavelength compared to blue and the other colors. So the long wavelength is red. The shorter is violet, but you cannot see them, we see blue. From our experiment, this formula here, we said that the fringe separation, the distance, in other words, the distance from the center to where the fringe is, will be determined by the wavelength. If you use a short wavelength, that means that the distance, the image will be close to the center. If you use the light whose wavelength is shorter, that means the image will be close to the central fringe. If the light used has the long wavelength, that means the fringe separation will increase. So from here, you can see red, since it has the long wavelength, it will be very far from the center. And if you draw this pattern here, this is our source now. We have S1 and S2, where we have now white. So expect here at the center of interference, because that's the point where we are combining white lights. The center here will be white. Why? Because we are combining white lights, and we'll be having white. The whole white from this source will be producing here, will be focused here. But when you go somewhere, the other parts here, there, or here, somewhere here, and then the intensity not necessarily to be having all the portion of light. Some of light will be consisting of some colors which will be the dominant here. And we see now from here, red has the long wavelength, should be found at the end, far end. Blue, which has a short wavelength, according to this formula, will be found near the central bridge. And then here, maybe down here, we'll be having red at the end. Here, in between, you can have other colors here. So you have V, I, but you cannot see them. So we say the center of interference will be white, followed by colored lights, whereby the bright light will be closer, near to the center, while red is far away from the center. So that is how you should know, when you answer the question, we are supposed to read the formula and this concept of wavelength. It's not easy to get the question where you are supposed to apply the formula direct, but you're supposed to use some knowledge on this concept of visible light. So the long wavelength here, according to the formula, is proportional to the fringe separation. It will be far away from the center, and the bright will be close to the central fringe. As a result, we have the central white at the center, while colored light from the center, having blue near the center, while red is far away. Those are the colors that we can see, but orange and the green, okay, orange, yellow, green, we cannot talk about this. We talk about the colors that our eyes are sensitive to. That's the second part of the question, where light has been replaced, monochromatic light has been replaced by white light, and this is the answers now from there. Part C. What happened now? When the whole experiment setup is immersed in water of refractive index 4/3, what will be the effects on the fringe separation of the fringes formed, given that other factors remain constant? We know the formula for the fringe separation is given by lambda d over small d. This is the fringe separation in air. We talk of A. This is in air. And when immersed in water, we know the wavelength will change. So you know from the refractive index of water from air is given by the speed of light in air over speed of light in water. This is given by lambda in air times the frequency, lambda in water times the frequency. So the frequency will be not changing. So you have wavelength in air over wavelength in water. So from there, you find the wavelength in water equals to n as a refractive index at A over n. So that's question number 2. So you plug here in the formula. So let's find the fringe separation now in liquid, in water, equals to the wavelength is given by, so this is our lambda in A, not n, it's lambda. So we have now lambda in water times d over small d. For this case now, our lambda is given by lambda A over n. This is n times d. This equals to lambda A d over d times 1 over d. So you can see the formula here is the same, but we have introduced a factor n. And we are given the refractive index of water is 4/3. So you have n d divide. If you divide by that, it means we are multiplying by 3/4, which giving 0.75 lambda d over small d. So you can see, since this number is less than 1, the fringe separation decreases. So the question, what will be the effect? The the fringe separation decreases since the wavelength of light is not changing, or has changed because it has been immersed in water from lambda to lambda over n, and because of that, the fringe will change by how much? 0.75 times this is the fringe separation in air. It has been decreased by that factor. Let's turn our attention now to example number 3. The question is, in an experiment using Young's double slits, it was found that the distance between the first and the 21st bright fringes is 2.5 millimeter. The distance from the first and 21st bright fringes, it can be either dark, but this is now talking about the bright fringes, is given. Now, and the fringe separation is given. The distance between the slits is 1 millimeter. And the distance from the slit to the screen where the images are formed is given as 25 centimeter. What was the wavelength of the light used? So, to start with this question, first, you should know that if you remember, we had this kind of experiment here. This is S1, this is S2, and that's where we had the center of interference, or so we said can have here or somewhere here. This is bright, which is given at the center, dark, dark, and then followed by we be having another dark somewhere. This will be bright. So the images are formed on either side of the screen. You can see from the either center of the screen. But the question now is asking about, this is the first maybe bright. The first bright and the second bright here. Let's find now the concept. The distance between the first bright and the second bright maybe is given as 5, maybe 5 millimeter. The distance here. How do you connect this distance with the fringe separation? So count. Since we have 2 fringes, and we have 2 fringes, so from which are here, we can see that now the distance between here, this is the second, so the distance from the bright to the bright, or the distance from the dark to the dark, as we have seen before. So the fringe separations are the same. The distance from the second bright to the first is what we call the fringe separation. And the distance from 2 successive dark or 2 successive bright is what we call the fringe separation. So this is taken as the fringe separation. But what happens if you are talking about the distance between the first and the third here? This is our third. Here. This is our third. Maybe that is our distance x. So count how many space do you have? So you don't count here. So you have 1, 2, 3 bright fringes. So the distance from the first to the third, we have 2 space. How do we get the space? We take 3 minus 1. So here is taken as y. This is taken as y. So you have 1, the first bright to the third bright. You take 3 minus 1, you get 2. So you have 2 spaces, which is given the name as the fringe separation, which will be occupying the same distance. So if it happens, we have 4, maybe, somewhere. There are 4. The first, so the distance from here, this is the first, this is the second, this is the third, this is the fourth, bright. And you know this distance is x. So the distance from the first to the fourth, you count how many spaces do you have? 1, 2, 3. So these are the 3 fringe separation. So the distance from the fringes can be associated with the fringe separation. So you can see here, if you are talking of the distance between the first and the fourth bright fringes, or either dark fringes, so you take 4 minus 1, you get 3 spaces in between, which is given the name the fringe separation. That fringe separation will be equal to the length, which is given as 2.7, okay, which is given according to the question. But here, 2.7 millimeter is the distance now between the first bright and 21st bright. You can see now we have how many spaces are there? 20 spaces, which will be occupying 2.7 millimeters. So from there, you see how you can associate the distance from the second or fourth between the fringes and the spaces in between them, or the fringe separation. So from here we know 20y equals, you can get the fringe separation. And after getting fringe separation, you use the formula to find the wavelength of the light used. Okay, let's start from here now. We have seen where to start. Our starting point is here. 20y equals 2.7 times 10 negative 3. You can find what is y here. What will be the fringe separation here? Is given by 2.7 times 10 negative 3 divided by 20. Using your calculator, you take 2.7 e power negative 3 divided by 20. So this gives us 1.35 times 10 negative 4 meters, since we convert those millimeters into meter. So you are comfortable that we know the fringe separation here. So the fringe separation equals to 1.35 times 10 negative 4. That is the step number 1. But this is not the question. The question is demanding to find what? You're supposed to find the wavelength of the light used. Since we know the fringe separation, the formula says the fringe separation is given by lambda capital D over small d. Provided we have this lambda is not given, the distance from the slit, the screen, is given as 25 centimeter, which is converted into this times 10 negative 2 meters. And the distance between the slits is given as 1 millimeter, which is converted as 1 times 10 negative 3 meter. So we have everything here. So you have y, which is given here. So you can find the wavelength. Let's check. We have 1.35 times 10 negative 4. That equals to lambda, which is not given here, multiplied by d, which is 25 times 10 negative 2, divided by our small d, 1 times 10 negative 3. So using this question here, maybe it's because we find the value here, but we have the value which has been found here. So equating the two, you can be able to find lambda. So making lambda the subject, from this formula we have 1.3 equation times 10 negative 4 multiplied by 1 times 10 negative 3 divided by 25 times 10 negative 2. You get something like, this is 135 times 10 negative 7 divided by 25 times 10 negative 2. Dividing, so we have maybe 1.535 over 25 times 10 negative 5. The powers will cancel out there. So using a calculator, you can find the value of the wavelength. 1.35 divided by 25 times e power negative 5. So the answer is lambda equals to 5.4 times negative power negative 7. Okay, that's the wavelength of the light used. So you can see now the question was given, and you are not given the fringe separation, but using the information we had from the question that the distance between the first and 21st is given as 2.7 millimeter, so that we can find the fringe separation. Remember, when we talk of the fringe separation, we talk of the distance between two successive fringes. It can be either dark or bright. And we are talking about the distance between the first and 21st. So you count the number of spaces which are around between the two. Between the fringes, it is 21 minus 1, which is equal to 20. And they equate to 2.7 millimeters, which you convert into meter. From there, you find the value of the fringe separation. Then, applying the formula, you can be able to get the correct value. So this is how you may be given different questions based on the Young's double experiment. So to make a summary of what we have discussed today, we have seen that when using Young's double experiment, the formula for the position of the bright, remember, this is the formula for finding the position of the bright, is given by n lambda d over small d. The orders n start from 0 and so on. This is the formula you should know. When you're finding the distance, or finding the position of the bright fringes from the center, you should know where do we start. If it's from the center, we start counting from here. N equals to 1. So that we have the first, because here n equals to 0, we get the position of the central fringe. And then for dark, we say that the fringe separation, so the position of the fringes is given by n plus a half lambda d over d. So from there, we have n equals to 0, 1, and so on. So from here, we see that when n equals to 0, that is where you can have the first dark. N equals to 1, you can have the position of the second dark, and so on. So using the two formula, depending on the nature of the question, you can be able to solve any question talking about the position of the fringes. But if the question is talking about the fringe separation, we saw that we can find the fringe separation or the fringe width using this formula. And we saw from this formula that the fringe separation or the fringe width will be increasing when the wavelength, when you have the long wavelength, the source of long wavelength, mathematically, where the fringe separation will be direct proportional to the wavelength. Also, can be increased by increasing the distance from the slit to the screen where the images are formed. And finally, you can find out the fringe separation can be changing when the distance between the slits is changing, either increasing. When you increase the distance, the fringe separation will decrease. When you decrease this distance, the fringe separation will increase. Now, you may be given a question to explain. This now as assignment. Take this as assignment. From here, the question is, using Young's double experiment, slits experiment, explain what happens to the fringe separation when, explain what happened to the fringe separation. To the fringe separation, in other words, the fringe width, when one of the slits is covered up. So let's check now if you can do that. Part B. The source slit is moved towards the double slits. Means the source slit is brought close to the double slit. Part C. And the fringe the slit separation is reduced to half of its original value. Okay, let's see now. This is the part of assignment. You can try to check whether you can solve those questions. And we have seen that where do we start? You should be based on the formula that we have derived. Using Young's double experiment, explain what happened to the fringe separation. You're talking about the fringe separation. So the main focus should be on the formula which connects the fringe separation. So our focus should be here. Y equals to lambda d over that. So from there you see what happens to this formula when one of the slit is covered up. Can you explain that? Remember the condition for producing interference, we said we must have two coherent sources, and the two coherent sources must be in phase or have a constant phase difference. If not the case, we cannot have interference when you have only one source. If you remember from the diagram we did, experiments from Young slit experiment, we had slits S1, this S2. Those are two coherent sources. Now, because of these two, the waves originate from the two sources, and we have the patterns interfering on the screen. So when one of the sources is covered up, it means we remain with only one source. So if the interference was produced here, the answer is the interference fringes disappear. So the answer is the interference fringes disappear. Why? We cannot have interference where having only one source. You must have two sources. Part B. What happens if the source slit is moved toward the double slit? In this experiment, these are the double slits. This is our screen. If you remember, at the back we had a slit here, which is giving us the source slit. And then from here we had the double slit. And then that's where the screen is. That is our D. That's where the image are formed here. Now, how is the distance on the image here, Y, affected by the movement of the slit, of the source slit toward the double slit? So you see from the formula, there is no connection between the fringe separation and this distance here. You are told the distance only will be affecting the distance between the slits and the doubles and the screen, and the distance between the slits here. There is no effect on the formula. But what do we observe here? In normal way, this can be observed in your experience. When you are very far from the source, your brightness, someone won't be able to see you clearly. But when you get close to the source, that means the brightness of the image will be increased. So the answer is no effect. There is no effect on the fringe separation. No effect. No effect on the fringe separation. Why? Because the formula is not involving the distance from the source slit. The formula is talking about the distance from the double slit to the screen, distance between the slits, and the wavelength. But the brightness of the fringes increases. What do you mean by that? If it's dark, bright. If it's dark, it will be dark. If it's bright, it will be bright. Brilliant, bright. So you can finish up part C, this as a part of an assignment. I think you have enjoyed our lesson. And the second part of this interference is coming. So don't move away. Stay tuned.